Hello everyone. In this session, I'm going to talk about how we can use boosting again for the regression purpose here, but this time the response variable is not a full-fledged continuous variable where I could have used L1 or L2 or robust or quantile regression. The response variable is a discrete response variable. So it could be a binary variable or it could be a multi-category variable, but it is a discrete. So in this case, how can I, so it could be an alternative to the binary classification itself, though it's not a classification in this case, it is still a kind of a, I want to use a regression model only in this case. So the output variable is a discrete response variable. I really want to assess how we can use boosting for this purpose. So in this context, I want to look at two different boosting algorithms. One is the boosting algorithm based on logistic regression. The other one is boosting based on probit regression. Again, because this is a categorical kind of a data, because I want to, the response variable cannot take almost every value. It takes only a discrete set of values. I am going back to my data set on diabetes. So I have loaded this diabetes data. I don't want to give more and more description of this. I know that there are some NAs or missing values as a part of this. So I am simply omitting those missing values by doing that na.omit, right? And I'm looking at the summary of this diabetes, which is having actually 564 observations after the omission. So this diabetes would be my response variable. All these six would be my attributes which I would be using as for the prediction purposes. So this one, again I have to load the mboost package itself. Everything is executed, all these are executed the mboost only. Mboost package, glmboost function, which we have used for our all our regular regression models as such. The same package and the same function we are going to use here also. So the code that we have copied during the continuous regression mechanism, that's the same code I want to copy again with just change in the family, all else remaining the same. But the data set is going to change here. So let me go back to understand from the slides. Logistic regression, we are using the package mboost, glmboost function. If you see here, this is the only difference. Earlier we were using family equal to Gaussian. If I wanted an L2 regression boost, then I had used Laplace. If I wanted L1 regression, then I have used Huber if I wanted a robust regression, and when I have used quantreg, it is more like I am going with a quantile regression. So these were the four regressions that we have used earlier for continuous response variable. But for a discrete response variable, I am looking at using binomial as a family with a link set to logit for logistic regression, and in the next slide you will see the same thing will be set to probit for a probit regression. Apart from that, both these mechanisms are one and the same. Looking at the model, this is more or less similar to what we have done earlier with our continuous regression itself. You load the package, get the necessary data into R. The difference is now the response variable is a binary categorical variable out here, right? I have to split the data into a training set and a testing data, right? So that's one step. Now the data got changed. 70% is 395. So I'm setting a seed value 1000. Then train is a sample from 1 to 564 where I am taking 395 observations with a replace equal to false. And my training data is a subset of diabetes with train rows that are there as a part of the train and all columns, and my testing data is again a subset of diabetes which contains the rows which are not there as a part of the train minus train, and I'm selecting all the columns. So I have my training data and the testing data in place. Now I am ready to fit the model. Right, you are fitting the model, you are setting the maximum number of iterations as well as the shrinkage parameter. Right, first let's read through this. After that we are doing the tenfold cross validation. We are getting the empirical risk estimation, and based on that we have to identify the optimal number of iterations where the error is going to be the minimum most. The empirical risk is calculated using the CV risk function. These are the same steps we have executed even in a continuous regression also. And I want to stop at those many iterations where the error is the minimum most. And the optimal model is used to classify the test data, and there we have some small changes because this is a classification data. I want to translate them into I'll get the scores, and based on that I want to classify the data. Less than this it goes to group 0, greater than some value it goes to group 1, and based on that the confusion matrix has to be printed and the error rate of the model has to be assessed. Up to there the steps are the same. So here I want to just make that small changes, the GLM boost. Now my dependent variable is diabetes, so I'll change that. Dot data is my training data, control is the boost control. Family, now instead of this I will set the family as binomial. Right, I will have to set the family as binomial with link equal to logit. I'll put it in the C function, link I will set it equal to logit. That's the main thing that I'm giving as a part of this model. Link is logit, and that is what I'm going ahead in terms of fitting the model. I think rest all should suffice for me. Let's go ahead and see if it can do the job for me. So I'm taking this data into R for the fitting purpose. I could not use GLM boost. Yes, I did not load the mboost library at all. Mboost package needs to be loaded. Right, now we have loaded this package. Now I think I should be in a position to use the GLM boost function. Yes, the family is binomial. I was able to use it. Now when I go with the fit and see, so you could see it's a negative binomial likelihood is the function that has been used. This is the last function when I am setting the family as binomial C logit. So this is the last function that is computed. Based on this you could see that the diabetes getting classified as a diabetes versus a non-diabetes is based on the months of pregnancy. There is a 0.06 weight given to it, glucose 0.013, the mass and the pedigree. So these are the inputs that are taken for the prediction purpose. Right, the model is built using these 4 parameters. The other 2 parameters, so there are 6 variables that we have considered. Only 4 of them are being considered as a part of the model. 2 of them did not get considered. When I am looking at the coefficients here, it looks like the same values I am going to get. Right, now I want to look at the fit CV, where I am looking at, are the 100 iterations good enough for me, or should I need to look at increasing the number of iterations or decreasing the number of iterations. So this is where I can look at the CV risk, where I am going with a tenfold cross validation. and based on that, see, whenever I get that the error is the least for the last one, it's better that I have to increase. It's an indication that I have to increase the number of iterations. So even here you could see the error started falling from 60. It looks like it has come to 47.19 at the 100th iteration. So the error is the least in the last iteration. It means that it's better that I have to increase the number of iterations also. So here I could see during the plotting, I got that for the 100th iteration itself, my error is the least. This is an indication that I have to go ahead in terms of increasing the number of iterations, but here I am not doing it. I am just giving you as an input. So the number of iterations I may have to increase so that I will get a much better one. Okay, so in this case, even if I have to stop, I have to stop at the 100th iteration itself, because that is the one that is resulting in the lowest risk. So this is an indication that when you are running the model, increase the number of iterations and run it, or change your new value, the shrinkage parameter. Try reducing the shrinkage parameter so that you get much better estimates as well. But as of now, taking that out, if I am going ahead with the prediction part, now here there should be one small change. If you look at the pred, and I am predicting it with the test data, so it is giving me some kind of a classification, right? It is giving me some kind of a classification, negative versus positive. Even if I set pred where I want to test type is response. Let me just check now. If I am giving type as response, let's see what the pred is giving. In this case, where I am setting the type is response, it will give me the probabilities between 0 to 1. So at least this will give me a kind of a base which says if this value is less than 0.5, I will set it as negative, and if it is greater than 0.5, I'll set it as positive. So I'm setting pred where I'm saying if else pred is less than 0.5, then set it as negative, else set it as positive. So these are the values that are going to come for the pred. So I could see this is how the pred is coming out, negatives and positives depending on whether the values are greater than 0.5 or less than 0.5. Now instead of this, so basically here, once I have done the prediction, this prediction I will set it as type equal to response, and once this has come out, I have to set if else. So I'll say pred wherein I am considering if else pred is less than 0.5, consider it as negative, otherwise take it as positive. And now I have to take it as a confusion matrix. So basically I will take it as a table between the pred, which is the predicted value, and the actual value, which is coming from the test data, the 7th column of the test data. So this is what is the confusion matrix that is coming out for me using this model, and this confusion matrix has resulted in an error of 36. 36 values are wrongly classified out of a total of 169. 133 values are correctly classified and 36 values are wrongly classified. So 36 are wrongly classified, indicating only 21.3% error rate, whereas in case of others the error, so probably if you try to compare these with our ADA boosting models that we have used earlier in the boosting itself for the binary classification, there the accuracies were only in the extent of 72, 73, 75%, resulting in a minimum of 25% error. Whereas here, this model, logistic regression, logic based logistic regression based boosting has resulted in an error rate of only 21.3%, resulting in this being a much better model compared to all others that we have considered earlier. So that's how we can use this model overall error rate to the extent of 21.3% based on the misclassification. And that is how, if this model is more and more a stable model, I can use this for the prediction purposes as well. Now the same logic, so here let me make a note of the error. 21.3% is the error that the logistic regression is giving on the testing data. Now the same logic, if I go with the probit model, if you see everything else is the same except the family is set as binomial. With the link, instead of logit, we are setting the link as probit. Otherwise you could see all these steps are exactly one and the same. So which means I can very well go ahead to that code, just keep copying the code by changing this logit to probit, and I should be able to execute the probit regression based boosting and see how the output is going to change. So let me execute the same here. So I'm running a probit model. This is the model for me. When I look at the fitment here, it looks like again these are the four parameters that are being considered: pregnant, glucose, mass and pedigree. So these are the four variables that are being considered as a part of building the model. And if I'm also looking at the 10-fold cross validation on this model to identify what is the optimal number of iterations. I've used the CV risk function to assess, to estimate the empirical risk of the model, so that I would like to look at that particular model where the risk is that particular number of iterations where the risk is the minimum most altogether. Now here if you look at the fit CV, the 10-fold cross validation model that got created out here, I could clearly see that the errors are going from 0.61 to 0.476. Again it looks like the error has been decreasing with the number of iterations. So overall it looks like at the 100th iteration only the error is the least possible, which I could see from the graph also. The 100th iteration is where the error is the least, which means it's better for me to try more number of iterations to see the best of the model. Even if I want to see at what iteration I should stop, it says at the 100th. Whenever we get the answer as 100, it always implicitly means that you better increase the number of iterations so that you will get at some point the optimal number of iterations for the model. So even here, just for the learning purpose, if I am sticking here itself and using this updated model for my prediction purposes. So these are the predictions that have come out. So I am converting those predictions into the values of negative and positive. And based on that, if I am making a confusion matrix using my table function, here the confusion matrix is coming out that 97 and 35 are correctly classified. 7 and 30 are wrongly classified, resulting in an error of 37 altogether out of 169, resulting in an error rate of 21.89% here. So this model has resulted in an error rate of 21.89% on the testing data, whereas your earlier model logistic regression was giving 21.3% itself. Overall, we could see that these two models have done a good job compared to the various AdaBoost models that we have used, boosting for binary classification kind of models. Compared to them, I could see that the probit regression based boosting or logic regression based boosting, both of them have given much lesser errors on my testing data altogether. So that's how we can use different sets of models, different sets of algorithms for different for different estimates on the data, and based on that we should be able to decide on which model is more and more appropriate for this data for the prediction purpose. Use that for the futuristic predictions as well. So as far as the discrete variables based regression method is concerned, I wanted to look at these two models. I hope you have got a fair amount of understanding regarding the usage of these these two models. If you have any further queries, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pagegurus.com. Thanks a lot for listening to this session. Thank you very much.